All right. So what we've seen in our last two examples is we had one where we actually have an interval. The idea is to write the limit as we go to infinity, as the limit as b approaches infinity. The key consequence, the key idea for both of these, though, is across whatever interval we're dealing with here, our function needs to be continuous. Right? It needs to be defined, so no vertical asymptotes inside of our stuff as we're doing these limits. And so the key idea here is that if we did an interval from negative infinity to some value, then we would write that in this case as the limit as b approaches negative infinity of the integral from b to a of f of x dx, or the other way, we're going from a to infinity as we've just done it here, the first examples. We would do it as the limit as b goes to infinity of the integral a to b of f of x. And then the third possibility is if you had, I'm sorry, I said that the wrong way. We already did that one. This is the wrong thing I wrote down here. This should be the interval from minus infinity to infinity, would be the limit as b goes to infinity of the integral from 0 to b, plus the limit as b goes to negative infinity of the integral from b to 0. That's if we were doing both negative infinity and infinity. Of course, we've already seen the other one that we do. Limit as b goes to infinity of the intervals a to b. But if we have the whole interval, then we would break that up as two separate. b approaches infinity, 0 to b, plus b approaches negative infinity of b to 0. And again, the underlying most important consequence of all this is that when we do these, f needs to be continuous across the whole interval. It will not make sense to do these if f is not continuous. Okay, so with that in mind, let's turn to another example. This time we want to do the integral from 0 to infinity of e to the minus 2x dx. Okay. So let's do that. That would be limit as b goes to infinity of the integral. I'm going to leave a little space there because I'm going to account for my substitution step here. The integral from 0 to b, and now e to the minus 2x. Okay, and now to carry that substitution through here, I would use u equals minus 2x. So du would call for minus 2 to go with dx. So I don't have that minus 2, so I need to account for it on the outside by multiplying by a minus 1/2. All right, and now this is ready to carry the substitution through. Limit as b goes to infinity of minus 1/2. And so integral of e to the u du would just be e to the u. So that's going to be e to the minus 2x, evaluated between 0 and b. Right? And then we start to work that out. Limit as b goes to infinity of negative 1/2. And then that's going to be e to the negative 2b, which means it needs to go to the bottom and become negative 1 over 2 e to the 2b, okay. And then minus negative 1 half, right? And then we're plugging in 0, e to the 0. Okay, and let's work this out. So here we're doing the limit as b goes to infinity. Well, e to a power, e is going to go to infinity there as b goes to infinity. So that's going to be a number 1 divided by infinity. So this whole thing right here is just going to go to 0. And then over here, minus a minus is just going to make that plus. E to the 0 is 1, so that's going to be a positive 1/2. And so therefore, this integral, the integral from 0 to infinity of e to the minus 2x dx, converges to 1/2. Converges to 1/2.